Okay, so last lecture we got a little baby intro to geometric optics. We talked about the basics of reflection and refraction. This chapter we get much more into the details, and I want to give you a game plan of what's coming up here. I'm splitting this content, this geometric optics topic, into 2 lectures because there's so much to talk about. And so in lecture 5.1, we're going to talk about reflection and refraction at a plane surface, so just a flat surface, and then specifically just reflection at a spherical surface. And then in the second lecture, we're going to talk about refraction at a spherical surface, which leads really nicely into thin lenses because those are curved surfaces on either side. And so then we can talk about lenses and all kinds of applications and stuff. So in this first part, we're just getting into reflection and refraction at a plane surface. And as you know, in geometric optics, we are adopting the ray model of light to figure out how light will form an image. So say we have some geometric object or system of objects that passes light. Our goal is to determine what image, if any, would be formed by light passing through it. To do this, we have to define precisely what we mean by an image and precisely what we mean by an object. An object in geometric optics is anything that radiates light. It may not be the original source of the light, which would be a self-luminous object. Instead, it may be reflecting light from some other source. So for example, your screen is emitting light, and this light is reflecting off of your face. Both your screen and your face could be objects. So what then does that leave room for to be an image? An image in geometric optics is a possibly non-physical representation of the object that the observer sees due to the way that light reflects and or refracts through a system. So if that didn't clear much up for you, then you're in the right place. So let's draw a little picture here. And what I'm going to do in this lecture is I'm going to draw quick pictures that I'm not worried about the precision of, because there are much better pictures that you can reference in the instructor notes version, the typed up version of this. So let's say we have some pond here, right? So that's water. And you have a little fishy down here, right? A little fishy. And that fish is going to act as the object that a person up here above the water sees. So this is just an observer person. And he's going to see that fish, right? But not so fast because there's an interface here between the water and the air. So the light just doesn't pass right through. We know that refraction takes place. So what happens with the actual light that's coming off of the fish, and this is an example where the fish is not self-luminous. I guess you can have a bioluminescent biological creature, but we're just going to say that the sunlight's coming and reflecting off the fish, but we don't care about that part beforehand. All we care about is that there is light coming off the fish in all directions, and the direction that we most care about is that it's coming off of the fish in this direction, which then is going to refract and make it to the observer, the human's eyes, right? But if you think about, if you're a human and you have human eyes and a human brain, you don't know that that this surface is causing the light to refract exactly in the way that it is according to Snell's law. Your brain's very powerful, but it doesn't quite understand all of that. It just is going to assume that the light was always coming in the same direction as it hit your eyes, right? So if you were that person, you would see the fish image right here. So we'll say fish object and fish image. This is the image that's formed by this object. So that's how it works when it refracts at that interface. Now, we could also talk equally about what the fish sees, right? Might as well consider that. So the light takes the same path this way as it does the other way, right? It refracts just the same. You probably verified that with Snell's law last lecture. And so there's light that's, again, coming off of the sun, and it's reflecting off of the human at all angles. That's how it works, right? So at all points of the human, there's light that's reflecting in all directions. And so that way we can talk about the human as acting as an object where it has light radiating from it. And so the one that we most care about is the one that makes it to the fish. And this is the real fish. And so the light that makes it to the real fish follows this same path here, and then it curves and makes it to the real fish, right? But the fish knows no better than you. And so it will assume, well, the light must have always been traveling in the same direction. And so it sees the human as existing in a straight line from where the light's coming from. So if this is the human object for what the fish is seeing, then this is the human image, which I should have drawn as a dotted line. The human image, right? It's not really where the human is, but it's where the fish sees that he is. And fish probably sees him as being some angry guy that's out to kill him. All right. So what we can talk about here is the difference between a point object, an extended object, a real image, and a virtual image. So in this image, we're really treating the fish as a point object, tracing one single ray from that point to the observer. All physical objects are extended objects, which just means that they're made up of many points. Extension of a single point, right? They have some dimension to them. Starting with point objects is a useful simplification, though, because extended objects can be thought of as just a bunch of point objects. So if you can understand the optics coming from a single point, then you can understand the optics as coming from any nearby points from that same object. As for the fish image, the human sees a virtual image of the fish because no light actually passes through the point where the human sees the image formed, right? So the human sees the fish image right here, but there is not actually any light that is forming a physical, real image there. It's a virtual image that he sees. Likewise for the fish observing the human. It is possible, however, for the image to be formed where the light actually passes through, in which case we would call the image a real image. And if that doesn't quite make sense to you because you're thinking, well, there must be light here because, like you said, there's sun coming everywhere and it's hitting all points and everything. That's not the light that we're talking about. We're talking about the light that is actually reaching the observer here. So it came from here and it intersected with the fish object. That light, none of the rays that are forming this image actually came through this fish image point physically. And if it still doesn't click, then we're going to see an example of where we do form a real image instead of a virtual image, and then it'll probably make sense then. So the case of the fish here was an image formed by refraction, but what we're going to start with is images that are formed by reflection, and then we'll later describe those formed by refraction. For both cases, we'll talk about a plane surface case first, like this air-water interface with the fish, and then about the spherical case. So, say we have a plane mirror with a point object and observer. So this is like as if you were treating yourself as a point and you were looking in front of a mirror. So I'm going to try to be consistent with colors, and this kind of thicker blue line here is always going to represent mirrors. And so I'll write plane mirror. All right, so that's always going to be mirrors, and then the object I'm going to try to always keep in red. So this is going to be point object, and we'll call it P for point. and I'll write object there just to make it explicit for now. And then over here, somewhere in this region, we're gonna, I'll tell you, there's gonna be an image that's formed. And it's gonna be a point image, because it's an image of a point object. And we're gonna call that P prime. So the image will always kind of, the notation I'll use is that in addition to the color difference, the image will be prime and the object will not be prime. But in order to find exactly where that image is, we have to do some work. So we know it's going to be there somewhere, but where exactly? So what we consider is that, oh yes, and one more thing is we're going to have some observer here. This is going to be like an eyeball, and that's going to be our observer. All right, so this is an object, and this is a person looking at that object, reflecting in the mirror. And so what we have to consider is all the rays of light that might be relevant to form the image and for determining what the observer sees. So using these example rays, I've talked about before as example rays, we can draw how the light radiates in all directions from the point object. And then we can use the law of reflection to draw what light will do as it reflects off of this flat surface from various angles. So let me do that here. I'm not even going to bother doing straight lines because I don't want you to be bogged down by me trying to get the perfect image, because you can just go to the text and see. So light is radiating in all directions, and so we can draw every single ray if we wanted to be here forever, but we'll just draw a few and then consider what's happening. So if this is hitting exactly in line, normal to the plane mirror, then it goes out this way, but it also comes back and reflects right back at the object, right? But this guy, if these are all coming out, right? This guy, whatever angle it hits that with, right? That angle of incidence, it's going to equal the angle of reflection. And so it may not be drawn very perfectly, but this should be the same angle, right? So that happens with all of these rays. So the best of my drawing ability, we're going to get this kind of a reflection image. And then down here, same thing, right? And you could draw maybe a couple more just to show the point. All right, yeah, so that's what that's going to look like. They're going to reflect off according to the law of reflection. Okay, so we see that this one here, that ray, makes it right to the observer, right? So it's going to contribute to what the observer sees. But again, just like with the fish and the human, the observer doesn't know that the light bounced off right here and reflected to reach its eye. Your mind, as smart as it is, can't do that kind of geometry and physics in real time. It has no way of knowing exactly how far a mirror is away, and it has no way of knowing that there is a mirror away. Think about it. If something reflects perfectly and all you have is the information of the light, how would you know that the light reflected? If you think about being in kind of like a house of mirrors, you're completely disoriented. You have no idea what are real objects and what are just reflected images. You got to kind of give your brain a break here. So it just assumes that the light was always coming in the same direction, which I'm going to do in yellow because it's not real rays happening here, but it's what your brain thinks is a real ray, right? And so all of these have, all of these have these kind of virtual rays that an eye would see. Right? The other way on this one. And it gets a little cross-hatched and confusing, but when I remove some of it, we will see there is a point here, if my drawing were perfect, somewhere right in there, and maybe we'll call it, actually, looks like it's right about here, right? So if I erase all the other stuff back here, there is a point, if my drawing were perfect, that it all converges at. So we would get all these rays are reflected as if they were emanating from this point back here. And this goes straight back to it. This one like that. Drawing isn't perfect, but if you're not convinced, you can look at the better drawing in my notes or the textbook. They all come as if they had emanated from a point source here. So think about, as a hypothetical just scenario, let's say that there was an object that was radiating light in all directions, and you're an observer back here, and there was no mirror in the way, then you would see that image perfectly clear with nothing happening, right? But that's not actually the case. The object is back here, right? And it's just reflecting. And so that's why we call this the virtual image. You're not imaging the actual object, you're seeing an image, a virtual image of the object. No light passes through here. There's no light behind the mirror at all. It's all bouncing off the mirror. So all back here is just blackness. There's no photons going on. But yet we see the object as if it were behind the mirror. And that's why when you look at yourself in a mirror, if you're 2 feet away from the mirror, you see yourself 2 feet behind the mirror or inside the mirror. That's how that works. You're seeing a virtual image. So there's a couple things that we can identify here as we move on and form a little bit more precise of an image. We have distances that we were just alluding to. So we have the distance from the object to the reflecting or refracting surface, in this case reflecting surface. We're going to call that the object distance. And we're going to denote that with an S. And then we have the distance from the reflecting or refracting surface again to the image. And we're going to call that S prime, and that is the image distance. And they, in this case, would be the exact same length. My drawing is not perfect. All right, so in this case, we would write that, I'll do it in white. The magnitude of S is equal to the magnitude of S prime. All right. So reflection at a plane surface, magnitude of the object distance is equal to the magnitude of the image distance. And you can verify this by noting that the two triangles in this drawing that I'm about to draw, so we have our mirror here, and we have this guy here, and we have the object, point object here, and we have the image back here, and supposing those are the same length, we have this, and it's going to reflect like that, and again we have same angle going on here, right? Law of reflection. And if you were then to connect to that point of reflection back to where the image is formed, that would be the same angle there. And you have similar triangles, right? They're congruent triangles. And so if this is the object distance, and this is the image distance, then you can tell that they are the same. All right, so for reflection at a plane surface, magnitude of the object distance equal to the magnitude of the image distance. So why specifically magnitude? Why did I bother to write the bars on either side? Because there are sign rules, and these will come back time and time again throughout this lecture 5.1 and 5.2. So I'm going to actually bother to try to type here. So sign rule 1 is about the object distance. All right, object distance. And it says that when the object is on the same side of the reflecting or refracting surface as the incoming light, then the object distance is positive. All right, so let's go back to this little drawing here. So when the object distance, so this red, or when the object is on the same side of the reflecting or refracting surface as the incoming light, the object distance is positive. So that just means that the incoming light is whatever is coming in towards the reflecting or refracting surface. So reflection or refraction. So this would be incoming there. And then these rays would be outgoing. They're going there. It's just a pre-reflection or refraction event and post-reflection or refraction event. That's what incoming and outgoing refer to. And so that's most often the case. And you might actually begin to ponder, in what world would the object distance be negative? Go ahead and hold that thought, because we're going to go over a scenario before this chapter is over where that's the case. All right, so then the next sign rule, there's 3 of them, is about the image distance. Image distance. So it says that when the image is on the same side of the reflecting or refracting surface as the outgoing light, the image distance, image distance is positive. All right, so very similar concept. So sign rule number 2 just says that if the image is on the same side as the outgoing light, then the image distance is positive. In this plane mirror reflection, it is not positive, because the image that's formed is on the right side of the plane mirror, right, in this region, but the outgoing light is on the left side of the mirror, in this region, right? And so that means that for a plane mirror, we have positive image distance and positive object distance and negative image distance. And that's why we had to talk in terms of just magnitude before, because we needed that negative sign to be accounted for. All right. When we get into refraction, then you have a different scenario happening where very quickly you have some material that light is refracting into. You might have a scenario where you have light hitting an interface and then it refracts inwards. And so you have incoming light and outgoing light. And this would be the object that the light is coming from, and somewhere in here, let's see. actually, this is the same deal as the fish. So then the image would be over here. So if this is P, and this is P prime, then again, it would be negative. So for this refraction event, then it would again be S is equal to negative S prime. All right. But that's at a plane surface, so refraction at plane surface. It's when the curvature comes into play that these things, that the other scenario with a positive image distance is seen. So we're going to get there. All right, so there's a third sine rule. And this one we're going to cover when we talk about those curved surfaces, because this one has to do with the radius of curvature. Radius of curvature. All right, so when these, I'll write it down, we won't talk about it for a little bit, and we're going to come back up to it, but definitely jot it down. When the center of curvature, denoted by C, is on the same side as the outgoing light, then the radius of curvature is positive. All right, so jot that down. We'll come back to it when we talk about curved stuff. All right, so one last thing to define before we move away from the plane mirrors. It's a very simple case, but there's one more thing that we can build up while we're still talking about the very simple case of reflection at a plane surface, and that is this concept of extended objects. So an extended object, as we mentioned before, is just an object with some sort of dimension, right? So we can actually determine the height of the image, and that would be if the object, let me draw this here, if we have, so this has nothing to do with our sine rule radius of curvature, just moving on to extended objects. If we have plane mirror here again, and instead of a point object, we have an extended object. It's really common to simplify an extended object to just a one-dimensional arrow. Same exact thing if you can figure out for a point, then you can figure out for multiple points. So if you can figure out for one dimension, you can figure out for multiple dimensions. So you just do an arrow. And so that would be your point. And I'll actually label it Y because it's more common. Y would kind of be, oops, I'll do this. Y would be like this distance here, the height of that arrow. And let's say that this is this is the center of that optical axis, is what we'll call it later. Then you can figure out the image, the extended image, oops, which we'll call Y prime, and the associated height of that extended image. So for each point of the arrow that we could consider, there's a corresponding image point. For reflection at a plane mirror, the image arrow is the same height as the object arrow, and you can verify that because we can just consider the tip of the arrow, a couple rays coming from the tip of the arrow. Let's see. So we'll do right about there. How not? Why not? So we'll do that. This one comes, and then it also comes back. And so then this one would reflect at the same angle again. It's going that way. And if you were to trace it back, I'll do here. I'll keep it white. If I've drawn this about right, then these two would intersect at the tip, right there. So that image point corresponds to this object point. And you could do the exact same thing for, I'll do it in this other color blue, for the bottom of the arrow. So one of them goes out and then comes back in. We'll do another one that goes like this. So it goes out and reflects at the same angle. I have to try to see if I can get my angles right, because this one is going to come back and intersect there and there, right? And if you were to consider any other point, right, if you were to continue on, new color, and just do midpoint of the arrow, you could do the exact same thing, going straight out, and then, you know, other example rays, and you would find that they all intersect at exactly the same point of the arrow on the other side of the mirror. And so by doing the top and the bottom of the arrow, you can really easily figure out how tall the arrow is. And honestly, we did not have to do the blue one, because if your arrow lies on the optical axis, then we know that it's just going to go straight across, and the bottom of the arrow of the image is also going to lie on the optical axis. And so from here on out, we'll pretty much, just for extended objects, need to consider the tip, the very tip of that object. And that will tell us, so if the tip in some, so if this weren't a plane mirror and it were some other refracting or reflecting surface, you might find that the image arrow is not the same distance and twice as big, right? So that's kind of going to be a theme, is we're going to find out the distance of the object distance, image distance, and the magnification is what that's called, of the image. And so while it's not that exciting for a plane mirror, we can still define this lateral magnification, which is given by m, of the object in its image. And so that would be y prime over y. And so since the object distance and image distance are equal, then we can say that the magnification is just 1, which is no magnification, right? It's like a multiplier. All right, so that closes it out. Next we'll talk about reflection at a spherical surface.